Okay, we're going to do some quick review on the whiteboard. I've got a couple of these for you. The first and foremost one, something you've seen before, it's the three-cell model. It really helps describe a lot of why we have the weather we have and why things move in the direction they do. So a couple things to remember. Again, three cells of the three-cell model are the Hadley cell, the Ferrel cell, and the polar cell. Hadley 0 to 30, Ferrel 30 to 60, polar 60 to 90. And they are just the same in the southern hemisphere, so Hadley, Ferrel, polar. So there's actually two Hadley cells in between the Hadley cells where your equator is going to be. A couple of things to remember always is that the surface winds in the Hadley cell actually flow from north to south, and then they rise and go the opposite direction. So think about that as a surface. That's why weather is generally going to be more predominant in that direction. Ferrel cell, surface winds move north to or south to north. Polar cells, again, north to south. So what happens is, again, so if the Hadley cell, surface winds are moving in this direction, Ferrel cell this direction, and polar cell this direction. Then you throw in the Coriolis force, where you know that everything in the northern hemisphere turns things to the right. So predominantly you have that north to south, but it's going to turn it to the right, so the winds are going to do that. And the Ferrel cell is going to turn to the right, it's going to go in this direction. And the Hadley cell here. So that's why the Hadley cell, the winds are called the trade winds, are also called, another name for the trade winds is called an easterly wave. And that's the winds that are going to bring hurricanes from east to west across in the trade winds. So those are called the northern trade winds. And the Hadley cell in the southern hemisphere is going to be the same thing. They're going to be coming that direction as well. Ferrel cell, winds are more westerly, the westerlies. And in the polar cell, the polar easterlies. So trade winds, westerlies, easterlies in the polar cells. Couple other fun little names here. Down here you have the intertropical convergence zone, roughly about 10 degrees north or south of the equator. Pretty slow moving air area. It's where the two Hadley cells will meet, because there's one here as well. Another name for that is also called the doldrums. Sailors used to call that because the winds were so light. Between the Hadley and the Ferrel cell, the horse latitudes, again, areas of, in between the zones are very, at the surface are very slow moving, calm areas. Couple other things, jet streams. There are actually two jet streams in the northern hemisphere. There's what's called the tropical jet here, and then the polar jet here. And we think more about the polar jet because it's what really affects a lot of our weather. Now, they're not necessarily straight lines like most. This is a model. Very zonal wind, meaning very west to east. Zonal means that it's complementing latitude, runs particularly with latitude. But these actually move more in a big giant wave. And I'll do that in red so it's easier to see. So the polar jet's going to run like this, tropical jet like that. They're going to be more south in the winter. But these waves of the jet stream are what are called Rossby waves. So you have your three-cell model, Hadley, Ferrel, polar, know the winds, know the directions, know the junctions in between those, and know the names of Rossby waves. And we'll be getting back in a little bit with a few more tips. Okay, so here's another very recognizable piece of meteorology data, and so it's called the surface station model or surface station model. And picture, if you will, a map of the United States where you have roughly 200 of these plotted about the United States. Those station models, that's where we're reporting their data approximately every 6 hours to put a cumulative data on the weather map. And there's a lot of information, and back in my day, long time ago, that information on a standard map would have to fit inside the size of a dime. So when you're handwriting this, now everything's digital, but a few things you should be able to interpret from this map. And I always reference a clock, so we reference certain symbols as far as the position on a clock. So if this is the center of the clock, so what are some of these numbers again? So here about 10 o'clock, that's going to be temperature, and that's in Fahrenheit. Down here at about 8 o'clock, 7 o'clock is the dew point. And we also know roughly, not perfectly, if you take the dew point and put it over the temperature, it'll give you relative humidity. So 6 to 8's roughly 75%. So right off the bat, we know here at this model, it's 80 degrees, it's 60%, 60 degrees is the dew point, which means the dew point, if the temperature drops to 60 degrees, that means the air is going to be 100% saturated. Because it's not, it's only 75% saturated, that's the relative humidity. This symbol here at 9 o'clock is the weather. So the different symbols, the two dots really just mean rain. They're asterisks, they may be snow. They're symbols for thunderstorms, etc., all in there. The center is just basically, what if you went outside and looked up in the air, what would you see? So let's say hypothetically, it's filled in 3/4 of the way. That would mean if you went outside and looked up into the sky is 75% covered with clouds, so that's your cloud cover. Here is a wind vane and wind barbs. Wind in meteorology, we use the term is where it's coming from, not where it's going to. So you're going to say the wind is out of the southeast, because that's the way it's pointing. Here's south, here's east, so the wind is a southeast wind. The barbs indicate how strong the wind is. Long barbs are 10 knots, short barbs are 5 knots, so this is going to be 15 knots. Again, and if it's only 5 knots, the barb's going to be like there, it's going to be short of that, so you'd be able to understand if it's long or short if they just don't put it out at the end. Here's pressure trend, so it's a downward line, so that means in the last 3 hours the pressure has been falling steadily. But you may get other symbols where it's like this. It means it's falling and stabilizing, it's rising and flattening out, or it's been stable. So that's what the pressure trend has done. This is how much it's actually fallen in those last 3 hours. And you have to remember, one is to move the decimal point over. So the pressure here has fallen steadily over the last 3 hours, and it's fallen 2.6 millibars in those last 3 hours. Up here is actually the station pressure, which is adjusted to sea level. And again, the average sea level pressure is 1,013.25 millibars. Pressure in North America is generally going to be trending between 1,040 millibars to 980 millibars. So again, here, if you're 986, first thing you have to do is you have to move your decimal point. So now you have a 98.6. And you have to decide, is there going to be a 10 in front of there or 9 in front of there? If I put a 10 in front of there, that's 10,098. That's way more than that, so that's not a possibility. So pressure here is 998.6, and that's in millibars. So you can get all that information out of that little piece of data. That's a surface station model. So we'll be back with you soon with a couple more tips. Okay. Another pretty common meteorological exercise are plotting isobars. So first, what is an isobar? An isobar is a line of constant pressure. And on a weather map, they are plotted every 4 millibars. So basically, if you started at 1,000 millibars, it would go 1,000, it would go 1,004, 1,008, 1,012, 1,016, if you will. Go in the other direction from 1,000 to 996, 994. Correct? 988, that type of a thing. So how do you plot an isobar? Not every station is going to be recorded as a multiple of 4 millibars. So in this exercise, we're going to plot a 1,004 millibar isobar. And everything's already been adjusted, so you're not moving any decimal points. The little dots are actually the station models. So first of all, you can find the 1,004 ones. It's a little bit of a connected dot. So if there's exactly that pressure, you can run the line, the isobar, right through those two models. Now here you're posed with a problem, because here's 1,004, I got to get my line to there, but lines of equal pressure never intersect. So I actually have to I know that somewhere between 1,006 and 1,002 there is 1,004. Not really sure where it is, but I know it's in between those two. So I continue on that line. Again, here's 1,006, so I know it's this side of that. It's like a topo map. So I can bring it here to my 1,004. Pretty straight shot up to my next 1,004. Up here again, here's a 6 and a 2, and I know it has to go in, it can't go between here, it can't go over here, it has to go in between those because you know somewhere in between there is 1,004 millibars. I'm turning the corner, here's a 2 and an 8. It's probably a little bit closer to the 2 and the 8 and the contour, so you bring it hug it a little closer, and I can bring it right back there. And that's how you would plot an isobar on a map. A couple other things to look at, again, just I rushed through this a little bit, but again, here's a pressure that's lower than 1,004, here's 1,008, and actually you could actually plot, there might be a 1,000 millibar isobar. Actually, my bad, because you know it has to be inside that. And then here's your actual lowest low, 998, and that's where you're going to put your low pressure symbol. So that's how you plot isobars. Every 4 millibars, connecting the dots, making sure that if it's not on the map, it has to go in between because you know 4 is in between there and between there and there. Hope that helps. Back in a little bit. Okay, quick review on fronts, some other map symbols. Fronts, there are essentially 5 that we talk about. First is a cold front, normally blue. They have little triangles. I like to think of them as icicles. You think of cold. Cold front is the fastest moving front of all of them. And again, as far as direction, the symbols are always on the side that they're going to. So this front is going in this direction. The warm front, very slow moving front, I like to think of them as remember little half sunshine. So warm front, cold front. Excuse me, the occluded front. An occluded front is when a cold front actually catches up to and begins to overtake a warm front. So that's an occluded front. Most rain here, second most rain here. Next one is a stationary front. That's when 2 fronts are lying next to each other. Kind of as a standoff, not one really, they're stalled, if you will, another term for it. So stationary front. And lastly is a dry line front, or also known as a dew point front. Sometimes you'll see it as a brown dotted line. Sometimes you'll see it where it looks similar to a cold front. Symbols, only it's going to be in brown. A dry line front or a dew point front is a front that separates moisture. So maybe not a lot of temperature difference between the 2 sides of the front, if you will. If we got rid of this, it was indicating a front. But maybe it's raining here all over and it's very dry here. So that's why it's called a dry line front. Another couple of symbols are what's called ridges and troughs. A ridge is the highest latitude portion of a high pressure system, and a trough is the lowest portion of a low pressure system. Sometimes you will see on weather maps troughs also marked with a dotted line, and they can be confused with dry line fronts. So fronts, cold front, warm front, occluded front, stationary front, dry line front. Fastest moving, slowest moving, most intense rainstorms, occluded the second most. These you'll probably get long, slow drizzles, not real intense, but kind of linger and hang for a long time. So that's fronts, ridges, and troughs. Okay, cyclogenesis, mid-latitude cyclones. We hear the term mid-latitude cyclones thrown out a lot, but you really know what it means? Well, we live in the mid-latitudes, the Ferrel cell, 30 to 60 degrees, North America. That's considered the mid-latitude. So when you hear mid-latitude cyclones, those are the cyclones, cyclone, low pressure, counterclockwise, that impact us here in the United States. So cyclogenesis means basically the birth of a cyclone and the evolution or life cycle of that cyclone. So again, mid-latitude, we live in it. That's the Ferrel cell. Beginning of it, you can see, we talked about earlier, so you have a cold front moving, which moves again faster. So you have cold air rushing in very quickly. There's warm air behind it, because this is a warm front headed in this direction. So what happens with that? You get storms along here. And the long line of storms like that, thunderstorms, would be called a squall line. So, and if you looked on a satellite picture, you're going to see this heavy cloud like this with pretty clear behind it. So you can visually see it. You can see that bow. So you know it's kind of moving in that direction. You may even see the little bit of the swirl at the top. So visualizing that squall line, cold front moving in. So what happens as that cold front, as it moves faster than the warm front, begins to catch up with the warm front. You get the top part, it becomes occluded. So you have intense rainstorms here, you have slow drizzly storms here, and that continues to spin around and catch up with. And usually right at the top, almost always, the very top of that occlusion, that's the center of low pressure. If you know low pressure turns counterclockwise, you can visually begin to get the feel of what's happening with the storm in cyclogenesis. So cyclogenesis is the life or the beginning of a cyclone. Cyclone, low pressure, unstable, bad weather, mid-latitude. It's happening where we live here in North America. So that's mid-latitude cyclones and cyclogenesis. Okay, thunderstorms. One of the big pieces of severe storms this year. Just a review of the 3 stages of a thunderstorm and why. So I'll sit back here, but have you already seen in some of the video clips, cold front comes in very rapidly. Cold fronts move faster than warm fronts. It has a very steep profile, if you will, versus a warm front has a very shallow one. So when that snow plow, that bulldozer, that freight train of a cold front comes rolling in very quickly, we know that cold air is more dense, so it pushes the warm air over top of it. So stage 1, as this cold front rolls in, pushes the warm air up, warm moist air, and we already know as air rises, it cools, it expands. If it's moist air, it's going to condense and create clouds. So level 1, or first stage of a thunderstorm, was called the towering cumulus stage, and it's predominantly all warm updrafts. That's part 1. So part 2, as we move along, so now it's developing. You get a lot of updraft, a lot of condensation up here. And what's going to happen now is, as it cools, cool air starts to get condenses, and you have cold air downdrafts starting opposite the updrafts. So you have updrafts and downdrafts, and that's going to be in your mature stage. That's when you get the most rain. This is going to be rain. As things are going up and down, though, too, you're getting a lot of collisions between raindrops and ice crystals and all that, and that starts creating static electricity, and that's where you get all the negatives here, you get your positive buildup down here, and that's where you're going to start getting your thunderstorms and your lightning. So the mature stage of a thunderstorm is when there's a balance between updraft and downdraft. Now what happens as this continues along is that the downdraft, actually in the rain, create friction on that updraft, and they start to break down the updrafts, and it becomes predominantly downdraft. And that's, thinking predominantly downdraft is going to be your dissipating stage of a thunderstorm. So stage 1, towering cumulus, updraft. Mature stage, updraft, downdraft, and final stage, the dying stage, the death of a thunderstorm is the dissipation stage. Now you'll get things out here during this mature stage, and this is what's called the gust front, and that's where the downdraft creates some wind out here. A couple other things occasionally with big thunderstorm clouds, you might get these bag-like clouds out in front of the anvil. Those are called mammatus clouds. Just know the 3 stages, and we'll get back to you very soon with a little bit more information. Okay, tornadoes, byproduct of a rotating supercell. They're really basically 3 stages of a tornado, very similar to a T-storm. There's the organizing stage. Maybe you start, there might be one just before that, dust whirl or dirt whirl. Not often, but that's pre. There's the organizing stage, and again, it's a funnel cloud until it touches the ground, then it becomes a tornado. So it's organizing. Mature stage, that's full stack, touching the ground, becomes a tornado, and then sometimes they might put something dissipating or shrinking in between here, between this stage, and there's the decay stage. So again, very similar to the tornado where you have the towering cumulus, mature, and dissipating. Here you basically have organizing, mature, and decay. A lot of times they'll call that decaying stage because it looks like a very thin rope. It's kind of like the cowboy with the lasso roping. It's very skinny rope with the whirl at the top. So you even call that the tornado is roping out. It's slowing down, it's breaking down, it's dying, it's decaying. So that's the stages of a tornado. We should know by now that with a T-storm, particularly with rotation, supercell, you get wind shear, and wind shear is levels of wind coming from different direction. But when you have that initial thunderstorm before it becomes a supercell, is that that gust front that comes down, you actually have the wind that's doing this. It's rolling. So you have downdraft coming over an updraft, and that makes that wind roll like that. And actually out in front of T-storms, you often get what's called a roll cloud. And it's because it's spinning between those two types of airs going like that. So you get this huge, very intense column of air that's rolling, but it's laying on its side horizontally. Well, what happens is you get the wind shear from different directions, and that actually brings that up vertically. So you need wind shear to tilt that horizontal air vertically to make a tornado. So the scale used is the enhanced Fujita scale. It goes from an EF0 to an EF5. The scale is based on damage that a tornado can do. So an extremely, extremely large, intense tornado going through a cornfield can actually still be an EF0. And then tornado, we'll get into Tornado Alley in a moment and come back as soon as I redo the whiteboard. So that's tornadoes. Okay, so tornadoes again, part 2. So we kind of learned why or how they happen on a kind of a micro scale. But let's talk a little bit about where they happen in the United States and what time of the year, etc., etc. So first of all, tornadoes mostly happen late spring, early summer. And why is that? Because we get the moist, warm air, which moist is tropical or maritime tropical, so moist, warm air coming from the Gulf of Mexico. You get the cold, dry air, continental polar, coming down from Canada. And thirdly, you have the jet stream, remember Rossby waves, pushing this from west to east. So you get this big mixing pole, and again, between the Rockies and the Appalachian Mountains. So you have this big mixing bowl of airs coming together, all that's at the right time, and they're coming far enough south because late spring, early summer, so they mix up in here, and this area is called Tornado Alley. And those are states like Texas, Oklahoma, Kansas, South Dakota, Colorado. Primarily, other pieces of other states touch that. So that's the giant mixing bowl for tornadoes in Tornado Alley. The secondary alley has become what's called Dixie Alley. And it's really below where the Appalachians kind of recede a little bit. But it's also the southeast United States is really heavily populated. So we talked about the enhanced Fujita scale where it's wind plus damage. Really, damage is the factor. Well, the reason a lot of the tornadoes out here are often rated EF1s and 2s is because there's not a lot of things to run into to create damage. Not that they're not strong, they're on the ground for a long period of time. But in Dixie Alley, a much higher concentration of people and property. So something that could have been an EF1 in South Dakota could be an EF3 in Atlanta or Jacksonville or someplace like that. So that's Tornado Alley. Those are the air, the mixing bowl, understand, between the Rockies and the Appalachians, the continental polar, the maritime tropical, and the Rossby waves of the trade winds, or excuse me, of the polar jet, all mixing this together and creating those differences, if you will, that make very intense storms. Okay, let's talk a little bit about lightning and thunder. And absolutely, Where there's thunder, there's lightning. And where there is lightning, there's thunder. Sometimes the lightning can be too far away for you actually to hear the thunder. So that heat lightning is just too far away. So for the sound to reach you. So where there's thunder, there's lightning. Where there's lightning, there's thunder. But basically some of the physics of lightning and what's happening with T-storms, and this is a static discharge, is that as we have that updraft and we have the downdraft, there's some collisions. There's collisions with water particles, with ice crystals, with condensation nuclei that create a static charge, just like rubbing a balloon against a sweater. There's also static, just of the pure atmosphere, the air moving against the ground. Again, more static build-up, separation of charges. So what you normally see in a thunderstorm cloud is the charges begin to separate as the positive charges go to the top, the negative charges go to the bottom. And also, because of that, the polarization of the surface at the ground. The ground is going to be more positively charged just prior to a lightning strike. When you start to get that positive charge buildup, that's literally when people almost feel like the hair standing up on their arm to the back of their neck. It's beginning to build and beginning to build and build. So some of the other physics, if you will, of a lightning strike. And there are really three basic types of lightning strike. They're what's called intra-cloud, so literally here to here, negative to positive. There's cloud to cloud, where maybe it's from here to here. And also cloud to ground, or ground to cloud is actually the same type of lightning. And for a long time, you always thought lightning was coming from the cloud down, but with high-speed photography and more technology becoming available, we actually see that the lightning is actually more ground to cloud. We just can't capture that with the naked eye. So what's happening, though, in this cloud is that it starts to create, they're trying to make a connection, and you'll see some of the first strikes, if you will, or false strikes, or what are called step leaders or leaders. And it's a feeler, it's a negative charge trying to find that connection, the positives. So the steps, and it'll go down in multiple branches all the way to the ground, looking for that connection. So that's called a step leader, the first part of the lightning strike. When it finally makes that connection with the bottom, the return stroke, often called an upward streamer. So you have step leader making connection with the upward streamer. And actually when they finally do make that connection, the lightning strike is actually going in this direction, not this direction. Just can't capture it with the naked eye. So you have your lightning strike, step leader to the upward streamer, and then that big discharge that gives you the lightning, gives you the flash. It's a sonic boom because the air is being superheated to 30,000 degrees, 5 times the heat of the sun. And that's that sonic boom, that rapid heating and contraction, or the thunderclap, if you will, that creates the thunder. Obviously, the speed of light is much faster than the speed of sound, so that flash to bang ratio, you could be up to 5 seconds before, if you're a mile away, you see the flash immediately. It could be up to 5 seconds before you actually hear the thunder. So flash to bang ratio is 5 seconds per mile. Also, after that initial strike, if there's left over a charge still remaining from that, you can get a secondary strike, which is called a dart leader, D-A-R-T, which is basically wound up following the exact same path that's laid out. So feeler down, bang, bang, left over, bang again. And that's lightning. Okay, this is a quick and easy one. Kind of a continuation maybe of electrical disturbances and even thunderstorms. Not until very recently did we even know these existed because of technology, our ability to fly at certain heights, take pictures, high-speed photography, many things like that. But it's a little bit of trivia, and it's not something I would dwell on, spend too much time on, but just know that they exist. They're called transluminous events, TLEs, and there's really two to know. What are called red sprites and blue jets. Think of this as a thunder cloud that's topped out at the tropopause here. And then again, it's not like we're flying every day on top of or even into the stratosphere with airplanes generally, or at the troposphere maybe. So it's not like we're up there a lot to catch these events. So, but what can happen? There can be some electrical discharges on top of a thunderstorm cloud, and so the blue jets illuminate very kind of a cone-like. Think of the end of a trumpet, if you will, if you understand what that looks like. So blue jets, and usually that are in the stratosphere. And then the red sprites, oftentimes a little higher, almost in the mesosphere, and sometimes as high as the thermosphere. And they look a little bit more like a mushroom cloud. Excuse my poor drawing, but they kind of expand up like that as they go up. So just know what they are, that they're both happen on top of thunderstorms. They're luminous events. And they may last for literally nanoseconds. So it's not like they're there for long. It's not like looking at a rainbow. They happen, and with the naked eye, you rarely can even catch it. So red sprites, blue jets, TLEs. Okay, a couple more terms I want to go through. There were on some recent tests, so make sure we all understand it. One is adiabatic or adiabatic, depending on where you went to school, cooling and heating. And really what that is that's temperature change based on change in pressure, and the change in pressure really comes from change in altitude. If you have a uniform parcel of air, and let's say all those little dots there are molecules of oxygen, nitrogen, and H2O, and so they're in this parcel and they're moving about and they're bouncing off each other, that Brownian movement, creating friction and creating a certain level of heat. And this really indicates the air pressure, column of air stacked on top of this. If we're at sea level, how many thousands of meters of air are stacked on top of this, and that pressure keeps it within that cell. So as that cell were to rise, let's say you went from sea level to 5,000 feet, there's less air on top of that parcel of air, so therefore there's less pressure on it, so that parcel can actually expand. So as it expands, the particles are further apart from each other, less likely to bump into each other, less heat. So with increase in altitude, comes decreased pressure, which also comes decreased temperature. So adiabatic cooling really ties into, we talk about lapse rate change. I'll get that in a minute as soon as I clean off the board. So that's what adiabatic heating and cooling. Again, if it's up here and it pushes down, so a parcel air is at sea or in Denver at 5,000 feet, and it gets pushed down without any other change, imparting any other thermal indicator or persuasions, if you will, on it, it's going to increase in temperature just because of the increase in pressure. So that's adiabatic heating and cooling. Another term you got to remember, you hear occasionally, is called latent heat. And that latent heat is the adding or removal of heat during phase change, but not necessarily temperature change, if you will. And it sounds kind of odd. But if you think about it, if you have ice, and so water in a solid form, you need to add heat to it to make water. But you can have ice at 32 degrees and you can have water at 32 degrees. But there is actually heat added to it here. So if you think about it, if you have liquid water, when it gets converted into ice, there is actually heat released, and that's the latent heat release from that. And so there's, in a conservation of energy, there's heat release there. Same thing as if when water vapor up in the clouds condenses to water, liquid water. Again, it's going through a phase change and it releases more heat, and now you have heat above cool. You have, and that's really what instability is, when air above things is warmer than air below things. That's not normal, and that's when they talk about instability, a little bit of inversion. So that's what latent heat is, and that's what adiabatic heating and cooling is. Back in a second with environmental lapse rate. Okay, the lapse rate. There's actually a dry adiabatic lapse rate. There's a saturated adiabatic lapse rate. There's many, it gets pretty confusing. So just want to try to keep this simple. And what simplistically we usually look at is what's called the environmental lapse rate, or the ELR. We know that there's varying levels. It's not a perfect system because it really depends on how much moisture in the air, different things, and how the rate of change. But in generally speaking, the environmental lapse rate, and we know with adiabatic cooling and heating, as we change altitude, we're going to change pressure. Because we change pressure, the temperature changes. So roughly though, for every 1,000 meters of change, you'll get 6.5 degrees of Celsius change, or if you use the English system, for every 1,000 feet of change, you'll get 3.5 degrees Fahrenheit change. So, as we had on the Solon test, I believe, so let's say you're down here, and it's 50 degrees, and you're going to take a walk up this mountain, and it's 2,000 feet from where you are to the level. So you're like, hey, do I need to, is it going to get warmer or colder? Well, we know for every 1,000 feet, you get a change at 3.5 degrees. So going up 2,000 feet, you're going to get a change of 7 degrees Fahrenheit. So without anything else changing, new fronts coming in whatsoever, we can extrapolate that and predict that roughly the temperature when you get to the peak of the mountain is going to be 43 degrees Fahrenheit. And that's the lapse rate. Okay, who doesn't just like to say the word haboob? Really? Pretty cool. So what is a haboob? A haboob is an extremely large sand dust storm, and they do happen in the United States, probably more often in the Middle East. But how does a haboob develop, and what causes it, and what are the issues with it? So think about first some type of thunderstorm happening out in the desert. Same complex, updraft, downdrafts. Oftentimes with these thunderstorms, though, they're almost like dry thunderstorms, is that the rain that's falling out of this thunderstorm cloud may actually evaporate before it hits the ground, and rain that never touches the ground is what's called virga, or precipitation that doesn't touch the ground. Well, you have the updrafts, you have the downdrafts. As it comes down, it either evaporates, but it's still a water vapor, and then it turns around and rises back up, which creates that updraft again, which pulls up all that sand and dust really back up to the very, almost to the tropopause. And that's why you can go up to 30,000 feet with this big, huge dust storm. Usually short-lived because it doesn't sustain its energy. That T-storm doesn't have the moisture recycling over and over and over again to sustain it. So haboob is a giant dust storm. Could be up to 30,000 feet, so it would affect planes. Very relatively short-lived, maybe an hour or two. And probably the biggest issue with haboobs is the visibility issues that it cause, car accidents, etc. It can cause respiratory issues if it sustains a lot. People are caught outside. But that's an haboob. Okay, let's talk a little bit about hurricanes. Let's see. First of all, extremely low pressure weather systems. Again, excuse my artistic lack of talent, but let's call this Africa, let's call this North America. Dotted line being the equator, next dotted line being roughly 30 degrees, so we're talking about Hadley cell. And we should know by now within the Hadley cell, the prevailing wind, what are called the trade winds, right? Or sometimes called the easterly waves. Easterly wave, say it again, easterly wave. And that's what's going to push these. So you start getting a little low pressure development off the west coast of Africa. Initially what's called level 1, which is going to be called a tropical disturbance. And this is turning again, in a, excuse me, counterclockwise fashion. But it's just a little low pressure storm began to develop off the west coast of Africa. Trade winds began to push it along. Warm Atlantic waters near the equator provide the energy to continue to develop this. They need to be at least 80 degrees Fahrenheit. That is why hurricane season is late summer, early fall. because it takes that long to heat up the water. Remember, the specific heat of water is much greater than that of land, so it takes a lot longer to raise that temperature, but also takes longer for it to cool off as well. So it needs to be the easterly wave, tropical disturbance moves, picks up energy from that 80 degrees, so that hot water begins to evaporate, rise in stability, weak shear. You don't want a lot of wind shear on a hurricane because it'll kind of chop the top off of it all. So as it progresses, it goes from a disturbance to a tropical depression. It gets stronger. Tropical depression, winds up to 38 miles per hour. And it continues to move westerly, and it's getting stronger and stronger and stronger. It gets over 38 miles per hour. It now becomes a tropical storm. Tropical storm anywhere between 39 and 73 miles per hour. And also, when it becomes a tropical storm, it gets its name. Every year, the National Hurricane Center creates names. They start with the letter A. They go boy, girl, boy, girl, boy, girl, until they run out. If they run out of names, they go to Roman numerals. Interestingly enough, if a hurricane were ever to cross over, let's say, Panama and into the Pacific, the name changes because Pacific hurricanes get to have different names than Atlantic hurricanes. Very much a rare factor. So as it continues along, it's moving towards us, the Caribbean. It's picking up energy, it's picking up speed. The wind speed gets up over 74 miles per hour, officially becomes a hurricane. The scale used to classify hurricanes is called the Saffir-Simpson scale. There's categories 1 through 5 based on wind speed primarily, but also does include central core pressure and storm surge is included in those three things. So it's not just wind speed, but primarily wind speed as it moves along. So as it gets closer to here, and again, it is turning in a counterclockwise fashion, gets stronger and stronger and stronger. There is something out here occasionally that helps steer this. This is going to be your Atlantic Ridge. Remember the high spot of a high cell, or the other name is called the Bermuda High. So Bermuda High can often be a steering mechanism depending on, it does fluctuate during the year, so depending on where it is, it could push it into the Gulf, or it could allow it to come up the east coast of the United States. A little bit of the anatomy of a hurricane. Again, the central core is called the eye of the hurricane. And generally, the smaller the eye, the tighter the eye, the more intense it is. It's like that figure skater closing their arms and they spin more rapidly. The outer edge of the eye is called the eye wall. It is the most intense part, and that's where the strongest winds are. Then you have rain bands along the edges, and actually there's a layer between the eye and the rain bands, and they call that the hurricane moat. Think of the moat like a castle surrounded by water. The rain bands, more water, so the moat is really between the eye wall and the outer rain bands. That's a little trivia for you. So it's turning in a counterclockwise fashion. It gets its energy from the water temperature. As it comes over land, it's going to lose that water, and it's going to get friction, and that's going to break down that hurricane. With Hurricane Sandy, Superstorm Sandy, also Frankenstorm Sandy, Sandy's path came along here, it turned up here, the coast, and rarity was this, there's another high up here, the Icelandic high, that was hanging out there, and generally at this time of year it's more to the east, but it was hanging right up there over Newfoundland, and that was really what was called that blocking high, and it's turning in this direction. Was one of the few things. 9 times out of 10, those hurricanes are going to turn out here and kind of die off in the northern Atlantic. With Sandy, that high was actually a little bit lower. It was here and made that turn into New York. Again, it was late in the year, October 30th, Halloween. It was also high tide, very populated area, which became a very dramatic storm. And also, after it gets to a certain position where the warm waters are no longer fueling it, it actually becomes what's called a post-tropical hurricane or a post-tropical cyclone. And in that particular case, it actually banded with another storm. So that's hurricanes kind of in a nutshell, so you understand how they turn, where they form, the levels, basic anatomy of a hurricane. All right. Okay, so we talked about squall lines already a little bit, but want to get a little bit more in detail about some of the winds produced by thunderstorms. And then we're talking about non-supercells because we know supercells actually rotate. But again, from a T-storm function, you have warm-up drafts, cold downdrafts. This heavy downdraft creates in the front edge what we call a gust front. That's that leading edge of wind of a T-storm. A long line of thunderstorms called a squall line. So they have that what we call straight line winds versus a tornado, which has a rotating wind. So when we talk about straight line winds, the kind of the catchphrase for all those could be considered downburst, because the wind's coming basically straight down and it's all in one direction versus a rotating mass. So how do you classify downburst? Well, a microburst is where that line of wind is 2.5 miles or less in width, if you will. So that's a microburst. A macroburst when it becomes over 2.5 miles. And in the cases of a derecho, which would be huge winds along a long extended squall line greater than 240 miles long. When we had that East Coast derecho, it basically covered 4 to 5 states at one point in time, traveled across 13 states. A derecho's combination needs to be at least 240 miles wide and have winds in excess of that same wind speed, which is severe storm wind speed, of 58 miles per hour. So, T-storms can produce straight line winds, downbursts. If they're less than 2.5 miles wide, they're called microbursts. Greater than 2.5 miles wide, macrobursts. In a case where the wind speed is exceeding 58 miles an hour, and that line is greater than 240 miles, it's called a derecho.